Good morning. This is Sumit Chandok. Today in this lecture, we discuss about the norm vector space. Say, first of all, we'll discuss what is the motivation behind the norm vector space. In many cases, a vector space X may at the same time be a metric space because a metric D is defined on X. However, if there is no relation between the algebraic structure and the metric, we cannot expect a useful and applicable theory that combines the algebraic and the metric concepts. To guarantee such a relationship between algebraic and geometric properties of Ax, we define on Ax a metric in D in a special way as follows. The first, we have to introduce the auxiliary concept of a norm, which uses algebraic operations of linear space. Then we apply the norm to obtain a metric D that is of desired kind. And this idea leads to the concept of a norm linear space. So let X be a vector space over the R, over the field R or C. A norm is a function having the following properties. Number one, norm of X is greater than or equal to 0 and norm of X is equal to be 0 if and if only X is equal to be 0. This is a positive definiteness property. Number two, the norm of alpha into X is equal to modulus of a alpha into norm of Ax for all X belongs to be the set X, for all X belongs to be vector space X, and alpha belongs to be real or complex. Norm of a X plus Y is less than or equal to be norm of a X plus norm of a Y. This is a triangle inequality. The pair X comma this norm function is called norm vector space. The pair is called a semi-linear space if it satisfies the second property and third, but not necessarily the first property. If X and Y belong to be the vector space X, then the number norm of X minus Y provides a notion of a closeness of the points X and Y in X, that is a distance between them, that thus norm of Ax is equal to be norm of X minus 0. Is the distance of function x from the 0 vector in Ax. So now we'll discuss some of the inequalities. So let P and Q in the norm space. Let P and Q be the positive real numbers and 1 is less than P less than infinity and 1 over P plus 1 over Q is equal to be 1. If P is equal to be 1 and Q is equal to be infinity, or if P is equal to be infinity and Q is equal to be 1, then we say that P and Q are conjugate exponents. The first lemma is let defined by the Young's inequality. Let P and Q are conjugate exponents with 1 less than P, Q less than infinity, and alpha beta is greater than or equal to 0. Then alpha into beta is less than or equal to be alpha raised to power P over P plus beta raised to power Q over the Q. If P and Q are true, then the inequality follows from the fact of a whole square, that the alpha minus beta whole square is positive, so we get the result. Also, if alpha is equal to be 0 or beta is equal to be 0, the result holds trivially. Suppose that P is not equal to be 2, then consider the function given by this, alpha raised to power P over the P plus beta raised to power Q over the Q minus alpha beta. Then alpha derivative of this function with respect to b alpha is equal to b alpha raised to power p minus 1 minus beta is equal to be q is equal to be 0. Then alpha raised to power p minus 1 is equal to beta, that is alpha is equal to b beta raised to power 1 over p minus 1. And using the property of a conjugate exponents, this is equal to be beta raised to power q over p, which is greater than 0. So now apply the second derivative test to the critical point alpha, and we get that the double derivative is equal to be this for all alpha belongs to be this. Thus we have a global minima at alpha is equal to be beta raised to power q by p, And it is easily verified that this term is being going to be satisfied. Now we will discuss the Holder's inequality for the sequences. So let xn and yn belongs to be the LP and LQ sequence where p is greater than 1 and 1 over p plus 1 over q is equal to p1. Then summation of the modulus of xi yi is less than equal to b summation of modulus of xi power p whole raised to power 1 by p into summation of yi raised to power q whole raised to power 1 by q. Now, if summation is equal to 0, then the inequality holds trivially. Assume that the series is not equal to 0. Then assume that this series is not equal to 0. Then for I is equal to be 1 to so on, we have the modulus of xi into the modulus of yi over the summation of xi power p whole raised to power 1 by p into summation of modulus of yi power q whole raised to power 1 by q is less than equal to b 1 over p into the modulus of xi power p or by summation of xi power p plus 1 over q modulus of yi power q over summation of a modulus of yi power q. This will come from our the previous result that we have the Young's inequality in which we have proved that alpha into the beta is less than equal to b alpha raised to power p plus beta raised to power q over the q. So we have used up this result to get up this inequality. So here we get now here. So we get this is being cancelled up if we took up the summation over here over the I. So we get this is less than equal to be 1 over p plus 1 over q, and you know that y because p and q are the exponent conjugates, and so y 1 over p plus 1 over q is equal to be 1, and hence we get the required result. So next is the Kashi's inequality is a particular case of this case when we consider the p is equal to be 2 and the q. Now we discuss the inequality. If p is greater than 1 and x and y and r sequence is an LP, then summation of xi yi power p whole raised to power 1 by p is less than equal to the summation of xi power p whole raised to power 1 by p plus summation of I is equal to be 1 to infinity modulus of yi power p whole raised to power 1 by p. So let q is equal to be p over p minus 1 if the summation of modulus of xk plus yk power p is equal to 0, then the inequality holds trivially. We therefore assume that summation of modulus of xk yk power p is not equal to 0. Consider summation of k is equal to be 1 to infinity modulus of xk plus yk power p is equal to be summation of modulus of xk plus yk power p minus 1 into the modulus of xk plus yk, and using up our triangle inequality in a modulus we have this is less than equal to p modulus of xk plus yk power p minus 1 into modulus of xk plus summation of k is equal to be 1 to infinity modulus of xk plus yk power p minus 1 into the modulus of yk, which is further less than equal to b. I just get terms like here. This term is being common up here, and this is equal to be the modulus of xk power the p whole raised to power 1 by p modulus of yk power p whole raised to power 1 by p, and this will be divided and multiplied with the q over the and q out there. So using up the property of exponent conjugates, so here the p minus 1 into q is equal to p, and this is equal to be this part, and dividing the both sides by the this part xk plus yk power p whole raised to power 1 by q, so this becomes equal to be uh, x summation of xk plus yk power p whole raised to power 1 minus q. So this becomes equal to be summation of xk yk power p whole raised to power 1 minus p by using the property of exponent conjugates. And then the right hand side we left only with this part, we get the result. Now we discussing some of the examples for a nonlinear space. So if R or C is a vector space over the R or C, then if we define the norm like a norm of Ax is equal to be modulus of Ax, then it becomes a norm linear space. You can easily verify the three properties of the norm. That is a positive, it's equal to be 0 if x is equal to be 0, and modulus of a norm of alpha x is equal to be modulus of alpha into the x, and alpha will come out, becomes a again satisfied, and similarly the triangle inequality is being satisfied. You can easily verify all the three properties here. So you can say that here, uh, say that norm of x plus y whole square is equal to be modulus of x plus y square, which is equal to be x plus y. If we take up over the complex into the x plus y conjugate, this is x plus y into the norm of conjugate of x plus y, and after multiplication this becomes a x into x conjugate, y into x conjugate, x into y conjugate, y into y conjugate, and using of the properties, so this becomes x into x conjugate. We know this is the modulus of x square, and this is a y into x conjugate is represented as x into y conjugate conjugate. This is the x into y conjugate plus modulus of y square. And you know that the z into the z conjugate is 2 times the real part of z out here. So this is 2 times the real part of x into y bar plus modulus of y square. So which is further less than equal to be, you know that the real part of Ax is less than equal to be modulus of Ax out here. So yeah, using about that property, we have this is less than equal to modulus of Ax square plus 2 times modulus of Ax into y bar plus modulus of y square, which is equal to be modulus of x square plus 2 times the modulus of x into modulus of a y bar plus modulus of y square. And you know that the modulus of y bar is equal to be modulus of y. So this is equal to be modulus of x square plus 2 times the modulus of x into modulus of y plus modulus of y square. So which is equal to be modulus of x plus modulus of y ka whole square, and which is equal to be norm of x plus norm of y ka whole square. So this is a triangle inequality is going to be verified out here. So let n be a natural number and x be a Rn or Cn for each x belongs to be having n tuples on x or s. We define the norm of x over the p, which is equal to be summation of I is equal to be 1 to n modulus of xi power p whole raised to power 1 by p, for 1 is less than equal to be p less than infinity, and norm of x over the infinity is equal to maximum of modulus of xi over the I. So now we have to check it out whether these two norms we have defined over the x are nonlinear space or not. So first of all, we will have to go with the first one, which is equal to summation of a modulus of xi power p whole raised to power 1 by p. So for each I is equal to be 1 to n, we have a modulus of xi is positive, and modulus of x summation of a modulus of xi power p is greater than equal to 0, or summation of modulus of xi power p whole raised to power 1 by p is greater than equal to 0. So it implies that the norm of a xp is greater than equal to 0. And for any x belongs to be x, norm of a xp is equal to be 0. Return implies that the summation of a modulus of xi power p whole raised to power 1 by p is equal to be 0. And it return implies that xi is equal to be 0 for all I is equal to be 1 to n. So hence x is equal to be 0. And number two, we have for any x belongs to be x and alpha belongs to be a field f, norm of alpha x p over the p is equal to be summation of alpha xi power p whole raised to power 1 by p. This becomes equal to be modulus of alpha power p into summation of I is equal to be 1 to n modulus of xi power p whole raised to power 1 by p, and this becomes modulus of a alpha into summation of a I is equal to be 1 to n modulus of xi power p whole raised to power 1 by p, which is equal to be modulus of a alpha into norm of a x over the p. It satisfies the second property. Number third property is the triangle inequality over the norm. So this is equal to be norm of x norm of x plus y over the p is equal to summation of a xi plus yi power p whole raised to power 1 by p, which is less than equal to be norm of summation of a xi power p whole raised to power 1 by p plus summation of a I is equal to be 1 to n yi power p whole power 1 by p. This is using a the inequality we have done up earlier. So which is equal to be norm of x over p plus norm of y over p. Hence, this is a required nonlinear space. So let x is equal to be a set of all bounded real valued functions on the closed interval a to b. If we define the norm like a supremum of a modulus of a xt over the interval a to b, then this norm over the x is a nonlinear space. Clear. So N1 and N2 are simple to be proved. Now we put the triangle inequality property here. So we have modulus of a xt plus yt, which is less than or equal to be modulus of a xt plus modulus of a yt. And using up a definition of the norm, we have a supremum of modulus of a xt plus supremum of a modulus of a yt, which is equal to be norm infinity and norm y infinity. So we get the answer out here. So supremum of or norm of x plus y over infinity is supremum of a modulus of a xt plus yt, which is less than or equal to be norm of a x over infinity plus norm of y over infinity. Hence, we can satisfy it. So let x be a set of a continuous real valued functions on the interval a to b, and if we define the norm is equal to the supremum of a modulus of a xt over infinity, and norm over the 2 is being defined like this: integral a to b modulus of a xt squared dt power 1 by 2. And both these norms are nonlinear space. You can easily verify that. So let x is equal to be LP and P lying between 1 to infinity. For each x is equal to be xi 1 to infinity, we define norm of ax is equal to be modulus of xi power p whole raised to power 1 by p. Then this is a nonlinear space. And similarly, L infinity is a nonlinear space if we define the norm as a supremum of a modulus of axi. So now we have a proposition is there. So let x be a nonlinear space, then dxy is being defined the norm of x minus y, then this defines the metric on x. So here the M1 and M2 and M3 properties are easy to see of a metric space. Now for any x, y, z belongs to be a x, we have a dx z is equal to be norm of x minus z, which is equal to be norm of x minus y plus norm of plus y minus z, which is less than equal to be norm of x minus y plus norm of y minus z, which is equal to be dxy plus dyz. Hence it is a metric space. So now this property next theorem will tell us about the relationship between the metric and the norm. If x is a norm-linear space, then dxy is equal to norm x minus y defines a metric on x. Such a metric d is said to be induced or generated by the norm. Thus, every norm-linear space is a metric space. Unless otherwise specified, we shall henceforth regard any norm-linear space as a metric space with respect to the metric induced by its norm. So we have already proved it of this part in the above example. If D is a metric on a linear space X, satisfying the following properties of a translation invariant and absolute homogeneity, then the norm of a x is equal to be dx0 defines a norm of x. So here dxy is equal to be norm of x minus y defines a metric. Here dxy is equal to be norm of x minus y is positive, and dxy is equal to be 0 return implies that the x is equal to be y, and dxy is equal to be norm of x minus y is equal to be minus of a 1 y minus 1 x is equal to be modulus of a alpha here is a minus 1 which is equal to norm of a y minus x which is equal to be dy x out here. So symmetric property is also being satisfied out here. Now we will deal with the triangle inequality. So dxz is less than equal to with its norm, and further we add and subtract the y. And using up a triangle inequality of a norm, this is less than equal to be norm of a x minus y plus norm of a y minus z, which is equal to be dxy plus dy. So dx plus z comma y plus z is equal to be d of a norm of a x plus z minus of a y plus z, which is equal to be norm of a x minus y. So which is equal to be dxy, and d of a alpha x alpha y is equal to be norm of a alpha x minus alpha y is equal to be modulus of a alpha into norm of x y. So we have defined, it is clear from this theorem that a metric D on a linear metric space, a linear space is induced by the norm on X if and only if D is a translation invariant and positive homogeneous. So thank you. In the today's lecture, we have discussed about the norm linear space and some of the examples related to a norm linear space. Thank you.